All right, welcome to Lecture 11, wherein we cover Chapter 3, Section 1. Let's get started. Formula masses. It should come as no surprise that a molecule weighs more than an atom, because it's made of multiple atoms. Okay? But how much does it weigh? Well, a single atom of hydrogen has, let's look at the periodic table. It has a mass of 1.008. So that's 1.008 atomic mass units. Now remember, this is the average. Okay? Some hydrogens are just a single proton. Some hydrogens are a proton and a neutron. Some hydrogens are a proton and two neutrons. So that's why the average is a little bit above 1. So a molecule of hydrogen is equal to 1.008 plus 1.008. On average, 610.2 atomic mass units. And water, H2O, is 1.008 plus 1.008 plus, we need to go to the periodic table, and we consult there, and we see that oxygen, 15.999. 999. And when we add those up, we get 18.015. And that is the formula mass of water in atomic mass units. Now, this is all fairly straightforward. What about ionic compounds? I mean, you can have an individual molecule of water. You do not have an individual molecule of sodium chloride. That's not a thing. Remember, this is just a ratio. Well, what we do is we deal with formula units. That is to say, we sort of pretend that the sodium chloride has a pseudo-molecule. A kind of molecule, a sodium chloride molecule. It doesn't, but we sort of pretend. And it works. The math works out exactly the same way in all the ways we want it to. And that's all that really matters. It lets us get work done. But sodium chloride would thus have a formula mass much the same way. So sodium, go to the periodic table, 22.990, and chlorine, while we're here, 35.45. 22.990 plus chlorine, 35.45. 0.485. 58.44 atomic mass units. So that is the formula mass. It's really, really easy to come up with. You just go to the periodic table, find the atomic mass, and add the atoms together. It works perfectly well for water, and it works just as well, even though it's sort of, a cheat. It's kind of a cheat, but it works perfectly for ionic compounds just as well. Why do we care about the formula mass? Well, take a look at this.
É a coisa mais linda que eu já vi passar.
Hydrogen will react with oxygen to make water. Specifically, you have 2 molecules of hydrogen plus 1 molecule of oxygen, making 2 molecules of water. We can't measure molecules, although it would be awesome if we could. Fact is that molecules are really, really, really ridiculously tiny. we have to work with what we can measure, and what we can measure is mass, such that 1 gram of hydrogen plus 8 grams of oxygen yields 9 grams of water. Roughly. This is rounded. What we need is some way to connect mass to molecules.
Ah, porque estou tão sozinho.
Or atoms, or ions, or formula units, or whatever we're working with. Okay, we need some way, whether quick and easy or slow and painful, to transition between what we can measure in the lab, mass, and what is actually interacting, reacting, working, and so on, which would be molecules, atoms, formula units, and so on. And that is where the mole comes in.
A beleza que existe, a beleza que não é só minha, que também.
So the mole is the measure of the amount of substance there is. Okay? It tells us how many molecules are present, or how many atoms, or how many ions, or formula units, or what have you. Whereas mass is the measure of the amount of matter that's present. And that's a pretty significant difference, because 1 atom of hydrogen is 1 proton and 1 electron. 1 atom of oxygen is 8 protons and 8 electrons. So this is going to have a lot more matter, a lot more mass, more matter, more mass, but same amount of substance. Only 1 atom. That's why when you react hydrogen and oxygen together, it's a 1:8 ratio in terms of mass, even though it's a 2:1 ratio in the other direction in terms of molecules. And the mole is what gets us there. The mole is sort of the go-between, in between the thing we can measure easily in the lab and the stuff that's actually interacting on the atomic and molecular scale. The way we get to the mole is through Avogadro's number. Avogadro was an Italian, and he was very interested in gas, and he found a way to sort of measure the amount of substance. He found the mole, more or less. And this is how he did so. Avogadro's number, N sub A, is equal to 6.022 times 10 to the 23rd per mole. Yes, this is a very big number that reflects the fact that atoms, molecules, and so on are very, very, very tiny. So let's see, that's 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. No, I don't know. Let's see, hundreds, thousands, millions, billions, trillions, quadrillions, quintillions, sextillions. So 602 sextillion, 200 quintillion atoms per mole, or molecules per mole, or ions per mole, or what have you. Okay, it doesn't matter. It could be a mole of pennies. Okay, if you had 6.022 times 10 to the 23rd pennies, you'd have a mole of pennies. That's more pennies than have ever existed, and are ever likely to exist, and yet you could theoretically talk about a mole of pennies. You could talk about a mole of popcorn if you wanted. That would be enough to cover the entire Earth to a depth of like 200 miles or something. But, you could. Now, the way he got this is neat. It's by measuring the densities of known quantities of gases. It's a Like I said, it's neat. We'll get to that when we get to chapter 9. But what this is based on is the number of atoms of carbon to get 12 grams of carbon. Because, by definition, carbon-12 is 12 atomic mass units. When you have an Avogadro's number of something, when you have a mole of something, that means you're going to have mass in grams equal to the formula mass in atomic mass units. So that makes for a very, very easy, sort of conversion. So going back to water, H2O, the formula mass is 18.02 atomic mass units. That means that 18.02 grams of water equals 1 mole of water, is equal to 6.022 times 10 to the 23rd molecules of water. So you can measure mass quite easily in the lab. That's what scales are for. You can't measure molecules at all easily. But if you know the mass and you know what substance you're working with, then it's a very simple and straightforward matter to know how much of the substance you're working with. In fact, in the lab, we never ever really bother to go down to molecules or atoms. We don't need to, because the number of moles is related directly to the number of molecules and atoms in a way that, mass just isn't. So we work in moles all the darn time. It's important that you be able to get between mass and moles and atoms, molecules, ions, formula units, whatever, okay? So here's how you do that. Going from mass to moles, you have grams on this side and moles on this side, and you have the molar mass in the middle. Molar mass. Molar mass is the same as the formula mass. We often, I'm more accustomed myself to talking about molar mass than I am to talking about formula mass. But formula mass is the more general term, so it's kind of better. So you can have the formula mass as well. And instead of talking about the formula mass in A and U, what you can say is grams per mole. So H2O has a molar mass of 18.02 grams per mole. H2 has a molar mass of 2.016 grams per mole. O2 is 32.00 grams per mole. And these all come straight off of the periodic table. Hydrogen fluoride. Well, hydrogen is 1.008. Fluorine. So fluorine is up here on the upper right, and it has a formula mass of 18.998. 18.998 gives us a molar mass or formula mass for hydrogen fluoride of 20.006 grams per mole. So converting in between mass and moles, you're going to use the molar mass or the formula mass. So let's say we have 10.00 grams of water, and we need to know how many moles of water we have. Well, the formula mass of water is 18.02 grams per mole. Now, we want moles. We have grams. We have grams per mole. We need grams to be on the bottom. We need moles to be on top. So what we're really doing is we're dividing mass divided by formula mass. But dividing is just the same as multiplying by the inverse. So 1 mole per 18.02 grams of water. So 10 divided by 18.02 gives us 0.5549 moles of water. It's pretty much that straightforward. Now let's say we need 0.250 moles of sodium chloride. How much salt are we going to weigh out on the balance? Well, that means grams of sodium chloride. And we're going to use the formula mass of sodium chloride. That's 58.44 grams per mole, for those of you who don't remember off the top of your head. Now, we have moles. We want to get to grams. That means we need grams on top. We need moles on the bottom. So we just multiply moles. So mass divided by formula mass equals moles. Moles times formula mass equals mass. So 58.44 grams per mole. Moles cancel, leaving you with grams. And what that leaves us with is how many grams? 14.61 grams of sodium chloride. So that's your conversion factor. Getting from grams to moles or moles to grams, you need the formula mass or molar mass. What about atoms, molecules, formula units, ions, etc.? Well, for that, you're going to use Avogadro's number. So let's say you have 0.125 moles of oxygen. That's going to be how many molecules of oxygen? Well, Avogadro's number is equal to 6.022 times 10 to the 23rd per mole. I've been leaving this blank this whole time because what goes on top changes depending on what you're looking at. It could be atoms, molecules, pennies. It's just items of whatever you're looking at. So in this case, it's going to be molecules. Now, we have moles. We want to get rid of it. Moles needs to go on bottom. So we're multiplying by Avogadro's number. So that's 6.022 times 10 to the 23rd molecules per mole. Moles cancel. It's going to leave us with molecules. Specifically, 7.51 times 10 to the 22nd molecules. Now, this is almost always going to be an incredibly, ridiculously huge number, just because atoms and molecules are so incredibly tiny. The exception would be if you were to continue pursuing chemistry and start working with, say, quantum dots or something, where you only have hundreds or thousands or maybe a few million atoms or molecules. Anywho, let's look at the other direction. Let's say we have 1.225 times 10 to the 24th molecules of, we don't need the of, CO2. How many moles of CO2 is that? Well, we're still going to be using Avogadro's number, but now we have molecules, we need moles, so moles needs to be on top. And 1 mole is equal to 6.022 times 10 to the 23rd. And we're dealing with molecules, so molecules of CO2. So molecule CO2 goes away. We're left with moles. And that gets us 2.034 moles. It's not times 10 to the anything, because these more or less cancel out. Not entirely, if you remember your math. But what that comes down to is it's the same as 12.25 divided by 6.022. So that's why it's just 2.034. All right, so to make it a little bit more explicit for the visual learners among you, so mass to moles, moles to and from items. So moles to items is Avogadro's number. Moles to mass is the formula mass. The question is, you're going to divide in one direction, multiply in the other, and there's that. And on the other side, it's reversed. Okay, mass divided by formula mass gets you moles. Moles times formula mass gets you mass. Moles times Avogadro's number gets you items. Items divided by Avogadro's number gets you moles. There is no way to get directly from mass to items. You have to go through moles. All roads lead to mole. And now you know why I usually write in print when I'm doing these. As bad as my handwriting is, you do not want me to write in cursive all the time. Okay, as with everything else, practice, 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 and you're going to need a periodic table for doing that practice. See you in the next lecture.